All right, here we are, Calc 30, no, AP Calc 30L. This is the AP class. We are digging back into your Stewart textbook here, 9.1, 9.2 differential equations. Now we did 9.1, which was antiderivatives in Calc 30 material. 9.2 is differential equations, which I'm going to explain today. When we take the integral of something, and that is the indefinite integral, if you guys remember, we always had to remember the plus c, right? And so if we forgot the plus c, it was a big deal. Now, the plus c represented some kind of constant that we were unaware of when we took the antiderivative, because there could have been a constant that the antiderivative of which was 0, right? And so now what we're going to do is we're going to explore particular differential equations with particular solutions. And so that means we're going to introduce initial conditions so that we can find out what C is. That's basically what this lesson's about. So let's talk a little bit about what is a differential equation. Many of the general laws of nature find their most useful form in equations that involve rates of change. These equations are called differential equations because they contain functions and their differential quotients. Okay, some examples of differential equations are dy over dx equals 2x. So this would be some rate of change, whether it's cost per unit, whether it's meters per second, population growth or whatever, people per year, whatever. So another one, dv over dt. So this could be velocity. Okay, the rate of change of velocity with respect to time. Okay, negative 9.8, and we'll do an equation that uses that. Actually, does negative 9.8 as a velocity, does it ring any bells for any of you physics students? Okay, so negative 9.8, yeah, so what is that? That's a gravitational acceleration kind of thing. So the derivative of velocity is acceleration, right? So yeah, gravitational acceleration. And then you might see something like p prime equals 3 times p. And again, I don't know what that one would necessarily be similar to. But think about this. The first one, like y prime, right, is 2x. And so in order to find y, we would take the integral of both sides, right? Or we take the antiderivative of both sides to find what y is. So this is what we have been doing. Take the integral with respect to y dx, the integral with respect to x as well. And so the integral and the derivative kind of cancel out. So we have y in terms of x here, and equaling 1/3 x cubed times 2. Does that look, 1 over 2 x squared times 2. And so this would be, y equals just x squared plus C. Some constant c. So that's what we would normally do, and that's where we left it because we don't really know what the constant was in the original question. Well, now we're going to introduce some initial conditions so that we can determine what c is. That's basically the big difference between this lesson and what we've done so far with antiderivatives. Okay, so let's just talk a little bit about this. For some reason, I have to move my notes over. General antiderivatives, that is indefinite integrals that we've studied before, have a plus c because the constant is unknown, with some initial conditions that are known, or without some initial conditions that are known. Particular antiderivatives can be known if there are some initial conditions presented. So particular antiderivatives can be known with initial conditions that are present. Okay, so it looks like something got erased down here. Equation with exact value of c included. Okay, equation of the antiderivative, I guess, of the integral. Let's say I think that was integral supposed to be there. Something got erased. Equation of integral with exact value of c included. Okay, that's the particular antiderivative. All right. So, for example, if we have something like y equals x squared plus c, but instead I know that initially we had x equals 0 and we had y equals 5. Okay, so that would mean that if x was 0 and y was 5, I could simply put in 5 equals 0 squared plus c, and then my c would come out to be 5, you see? And so the particular antiderivative with these initial conditions present would be y equals x squared plus 5. And that it should make total sense, because when we're talking about a parabola that we don't know, where this parabola sits, if it's up, down, it's x squared something. But now that I know that this is an initial condition, the 5, well then I know that my parabola has to go through 0, 5, and so this is the exact equation of the integral sort of thing. Okay, now we'll talk more about that as we get through, but that's the general gist of it. Okay, so we can solve a differential equation. That means we can find f of x if we're given f prime of x, or if you want to call that capital F, right? But f of x would be the antiderivative, or the integral of f prime of x, when given a set of initial conditions. This will give us the particular solution, not just a general one. So the general has the plus c, remember, and particular gives an actual value for c. So those are two important things to remember. General is plus c, and particular gives us an actual value for c. And just to show again what I mean, here are three options for x squared plus c. We don't know what the c is, so it could be up, down, could be 0. But now that we know we have a specific set of conditions like this example, we know where it is. And another one, if we are given the point on the graph of 1, negative 3, okay, 1, negative 3. Well, that's a little bit different than our previous example. So what would be the c value if we had 1, negative 3? So here is 1, and here is negative 3. So you see how it could be this one right here, right? So it could be this actual parabola. And how do we find out what that constant is? The constant's not going to be 1, it's not going to be negative 3, it's going to be some constant that brings us down the y-axis there, right? And so it's not either one of these values, but instead what we do is we simply put negative 3 equals, 1 squared plus c, and we solve for c. So we plug the initial conditions into our general form of the antiderivative, and we're going to get negative 3 equals 1 plus c, and we're going to have c being, looks like negative 4, when we subtract 1 from both sides. So that means this comes down 4 units here. So this is negative 4 here, and therefore the actual particular equation for that solution there, for the differential equation, is this right here. So solving a differential equation is not, and I should have mentioned this at the beginning, but you're not solving for a variable, you're solving for what is the original function. Okay? You're solving for what is the original function. So any questions so far? All right, so solving differential equations, we're solving for the original function that yielded us that derivative. Okay. All right, 9.2, differential equations with initial conditions. Okay, so this is from your textbook. Let's do example 1. I have some steps here on the side. So let's do this. Now this is going to look very similar to what we've done. This ds over dt equals dt is the same as the the 2x in the examples above. So this is going to be very similar to what we've done already. All right, so our steps. I'm just going to make these a little bit smaller so I can fit them all on the screen nicely. Let's see, not size 36, let's go 25. Okay, and then I'll just squish those up a little bit. Okay. Okay, so again, solving for differential equations, solving means to find s given s prime in an equation, okay? Or solving for f given f prime, right? So we're actually solving for the original function. And if we're given initial conditions, we can have a particular solution, a particular function that has the c value included. All right, so the steps, what we're going to do here is we're going to, I'm going to write this as s prime equals 2t. Okay, so ds dt, I'm just going to write Newton notation there. Okay? All right, so what we're going to do is we're going to integrate both sides. And we're going to integrate with respect to the variable. So this is integral of s prime dt. This is integral of dt, 2t dt. Okay, so we integrate both sides. And remember, the properties of equations, what you do to one side of an equation, you should do to the other to maintain the equality. So we're definitely going to be taking the derivative of both sides. So you want to have your s prime or your ds dt all alone on one side so you can take the derivative. Okay. Now, when there's going to be other variables involved in the next level, so I'm going to tell you how to separate those. That's going to be separable differential equations. That's next lesson. Okay. So right now you should just have one variable. You get the s prime by itself. So if we take the derivative, this is now going to be just s, right? The derivative, the integral of a derivative just gives you the original function sort of back there. And so that's going to be s. The integral of 2d dt, that's going to be our 2 times 1/2 t squared. We add to the exponent there. We divide by that new exponent and so on. So we have s equals t squared plus c. And please remember your plus c at this point. So this is where we would stop if we just had a general antiderivative with no limits of integration, right? If there's no numbers here, this is normally where we would stop. But because we do have initial conditions given of s equals 3 and t equals 0, we can then find out what c is by simply plugging those values in. So s is 3, so I'm going to put 3 there. T is 0, I'm going to put 0 there. And this is really easy, isn't it? So c is 3. Okay? So how are we doing with our steps here? Integrate both sides, insert initial conditions, solve for c. Okay? So we've done that. And now we simply rewrite the complete particular antiderivative function. And so my solution then is going to be s. Now you could write s of t if you want, right? The function notation there equals, we're going back to this one here, right? And including this c value up there. So equals t squared plus 3. All right, the initial conditions help us to know what the constant was that we took the derivative of, because the constant is just going to be a derivative of 0, right? So now we know what it is. And over on the side here, I do have, some examples here. There are an infinite number of possible solutions. So if we know what the initial conditions are, in this case 0, 3, the actual one of the solutions that passes through that point is the particular antiderivative. And so this is the t squared plus 3. Okay, so the one highlighted in red there is the particular solution. How are we doing? Good? I think this is pretty easy stuff, isn't it? We've done 90% of this stuff. Now we're just including some values for the variables now and solving for c, and right? Yeah. Not too hard. Okay, that's good. It doesn't get much worse than this. Let's try another one. It doesn't really get much harder than this for this round. Next lesson, we'll up the ante a little bit, okay? So example 2, you want to write this down in the notes that I've given you there. And if you don't have the notes or lose them, you can always print them off the website, mrmathwell.com. Go to your AP Calculus page, and you can print off another one. And watch this video. Okay. So, again, the differential equation that we're given is dy over dx equals 6x squared plus 6x. Okay? Awesome. All right. Find the function y equals capital F of x. Okay, so this is, I know I have y here, but this is the antiderivative, right? So this is the integral here, or the integral function. Integral function. From the antiderivative, we're going to take antiderivatives here. That passes through -1, 0, so these are initial conditions. Right? And this, of course, is your differential equation. All right, so we understand the setup of the question here, hopefully. All right, so our steps are on the right again. So we integrate both sides. So I'm going to write everything out here. Okay, so the integral of dy dx and the integral over here of 6x squared plus 6x dx. And yes, please show all of this notation. I'm trying to model this for you, so please make sure you show each of these steps. Okay, don't cut too many corners here. Show that integral that you're actually integrating both sides. Now the integral of a derivative, okay, just gets our y value back, so y seems to be the function there. Now this, I take the antiderivative here, so that's going to be 6 over 3x cubed plus 6 over 2x squared plus c. Sorry? You okay? Okay. You were agreeing with me. Oh, okay, sounds good. No, hey, let me know if I write something down wrong. I don't have any of the solutions with me. I'm just going off the fly here. That's the way I roll. So if I make mistakes, I actually don't mind because you guys are supposed to catch them. Right? All you brilliant minds out there, right?
Yeah.
I don't mind that. Okay? So we want to find out what the c is. So -1 is going to be our x value, and 0 is going to be our y value. So 0 equals 6 over 3 is 2, so 2 times -1 cubed. 6 over 2 is 3 times -1 squared plus c. So this is going to be 0 equals, that's going to be -2 plus 3 plus c. 2 minus 3 is going to be over on this side, and so we have -1 equals c. Does that look good?
Yeah.
Awesome. Okay, so now we'll rewrite the equation, and again, this is what we're rewriting really, right here, with the c now being -1. It's easy as that. So y equals, and yeah, y seems to be our function name there, so y equals, I'm going to simplify this obviously, right? 2x cubed plus 3x squared minus 1. And that should be our solution, okay, the particular solution there. All right. Now what I'm going to do is I'm going to graph this, okay, and you guys can, you can always check on Desmos or check on graphing calculator that you have, check to see if what you did was correct, because they're going to get a little bit more complicated than this, believe it or not. But what you want to do is you want to graph your solution right here, your answer, graph that. It's going to be a cubic function here, right? And then make sure that the point -1, 0, okay, goes is on this graph, okay? Now you can also double check to take the derivative of this and make sure you get your original equation back, okay? Obviously to check to see if you did your antiderivatives correctly, right? So this would be 3 times 2 is 6x squared plus 3 times 2 is 6x plus 0. So that's the same as what I started with. So I did my antiderivative correct. So let's just check the graph there. All right, so if we graph this on Desmos, what we see is we have this as our graph. And what was our point that we're looking for again? -1, 0. Okay. And so it looks like right here, I do have a point -1, 0 that is on this graph. So that is the graph. All right. Now, if I were to, let's say I'm going to copy this, okay, and I'm going to make this a plus c, and we'll take a slider for c. So you can see that this general solution would have the same shape, but we don't know what the c is. So it could be moving up and down. It could be any one of these, right? Any one of those. The only version of this that goes through our initial condition is that one. And so that's why we have it. But without that initial condition, it could be any one of these. Now, what I'd like you to notice too is that if we were to draw a tangent line, okay, let me just clip this and bring it over. If we were to draw a tangent line, before I get to this next example. Now, these are just two such cases here, but if we were to draw a tangent line on these graphs, that at any x value, the tangent line would be exactly the same, right? Even here, this tangent line is exactly the same slope, not the same line, but the same slope. It's always the same slope given any x value. So this one's super large, this one's super large. Okay, you see that?
Yeah.
So this is why the derivative, 6x squared plus x, that's why that works for any one of these possible solutions. Because no matter what x value you put in, you'll get the same derivative, right? But to find the actual equation that we start with, we need to plug in the initial conditions to highlight that this red one is the actual graph that we're starting with. But again, this derivative works for any iteration when you have a plus c here, it works for any graph, any of those graphs, because you'll have the same tangent slope, right? For all of the graphs, the same tangent slope. Make sense?
Makes sense.
Okay. Now I think I explained that too in Calc 30 when we just kind of did the plus c, like this is why, plus c can move up and down. And I think I did explain that too, so. All right, so here's another easy one. Yeah, if we have ds dt equals 9.8t, now this could be the derivative of a position function given with respect to time, okay? Or let's say, or some anyways, doesn't matter what it is. But if we do this, we take the integral of both sides, okay, with respect to t, because that's the variable that I see, and that's the variable that's down here, and that's the variable that's in this equation. And so this turns this into just an s equals, now this t up to the 1 is going to go to the 2, and so this is going to be t squared, and this is going to be 9.8 divided by 2, right, plus c. So s is 4.9 t squared plus c. Initial conditions of 0, 0. Okay, so the position 0, time is 0, let's say. I have 0 equals 4.9 times 0 squared plus c. That means my c equals 0. Not very interesting, but still valid. So I have now s equals, I go back to this and I put in 0 for c, s equals 4.9 t squared. That's it. Okay, so sometimes your constant will be 0, no problem.
Okay.
Capiche?
Capiche.
All right, I don't think I have any extra, any more examples on your notes package there. So here it is. This is differential equations part 1. There are 2 assignments here, some from the Stewart text, also some from the Finney, so you have a good chunk of time here this class to work on this assignment.
Okay.
There it is. All right, and before you leave this lesson, go ahead and try this AP exam question. This is a question that you will see on the AP exam. Pause the video and give it a try, and I'll show you the answer in a second. All right, here's the answer. If you got E, you are correct. Differentiate both sides, plug in your initial conditions, solve for C, and this is your particular solution to the differential equation. So that's your example for your AP question. See you later. Math is awesome.
You put 60 to 30, you put 60 during there instead of 60.